First, we're asked to balance this equation. On the reactant side, we have a hydrocarbon, we have oxygen, and on the product side, we have carbon dioxide and water. So this is known as a combustion reaction. Specifically, it's called a complete combustion because all you get is carbon dioxide and water. To balance a complete combustion of a hydrocarbon, you can do this quickly by recognizing that carbon only appears in the hydrocarbon and in carbon dioxide. Therefore, the coefficient in front of carbon dioxide has to match the subscript of next to the C in the hydrocarbon. Next, you can recognize that hydrogen only appears in the water molecule and in the hydrocarbon. Now, in the water molecule, it's always H2O. So the coefficient in front of the water molecule is going to be half of the number of hydrogen atoms, or the subscript next to the H in the hydrocarbon. Finally, the coefficient in front of the oxygen molecule is going to be the number of carbon atoms, which is 5, plus 1/4 or a quarter of the hydrogen atoms in the hydrocarbon, which is 3. So the coefficient here is going to be 8. And that has to do with its relationship, obviously, to the oxygens in the carbon dioxide and water. In the carbon dioxide, it's in a 1-to-1 ratio, O2 and CO2. And C is also in a 1-to-1 ratio with the hydrocarbon. And in terms of the oxygen in the H2O, there's only half as many O's in the H2O as there is in O2. And then that's connected to the H, which is half of the H's in the hydrocarbon. Now, let's go on to interpreting the balanced chemical equations. Now, several ways you can interpret a balanced chemical equation. The first way you can do is by interpreting these coefficients. Let me put a 1 here just for visual purposes. We got 1, 8, 5, and 6. You can interpret those coefficients as moles. That's where we get mole ratios from. So, for example, you can interpret this equation as saying 1 mole of C5H12, which could be pentane, C5H12, reacts with 8 moles of oxygen gas to produce 5 moles of carbon dioxide and 6 moles of water. That's good. You can also interpret this in terms of volume if they're gases at STP. So that's important. You can't interpret solids or liquids as volume, but you can do that with gases. So, for example, you can say 1 liter of C5H12 reacts with 8 liters of O2 to produce 5 liters of carbon dioxide and 6 liters of H2O. That's good too. And of course, I just arbitrarily picked liters. You could have picked gallons, milliliters, or 22.4 liters, and they're all related in terms of volume if they're gases. Now, the one thing you can't do is interpret these coefficients as masses. So, for example, you can't say 1 gram of C5H12 reacts with 8 grams of O2 to produce 5 grams of carbon dioxide and 6 grams of H2O. That is not true. That is never true. Because the masses are specific to their substances, their intensive properties, the molar masses are. So you'll have to use information on the periodic table to get molar mass information. Let's see. You can also interpret these as molecules if they are molecules. In this case, these are all molecules. So you could say, for example, 1 molecule of C5H12. All right, I'm not going to just keep writing this over and over again. Reacts with 8 molecules of oxygen to produce 5 molecules of carbon dioxide and 6 molecules of water. That's fine too. And if these are not molecules, you can use whatever representative particles they are, such as atoms or formula units if they're ionic compounds. And now let's answer the last part. Masses of reactants and products. So one reason we balance equations is to obey the law of conservation of mass, which boils down to the number of atoms. So the simplest form of matter is the atom that retains its identity, are elements and atoms. So the number of carbon atoms on the reactant side has to equal the number of carbon atoms on the product side. So reactants, right? The number of atoms of each element must equal the number of atoms of each element on the product side. And because that is the basis of mass, mass of the reactants must equal the mass of the products. Right? So you can see why this statement earlier is false. 1 plus 8 does not equal 5 plus 6. Now, it might coincidentally equal in some equations, but that's not how you interpret it. You've got to add up the individual atoms and balance them out, and then the masses will balance. Right? For example, if you had 10 grams of all the reactants and they undergo a chemical reaction, then you're going to have 10 grams of products. And those are all the ways I can think of at this time in terms of how you would interpret a balanced chemical equation. Probably the most common way is going to be, if you're doing stoichiometry, is going to be interpreting these coefficients as moles. And then if you're working with gases, they can be volumes. A couple more things I want to add before I wrap this up. So looking at this comparison, atoms are conserved. Mass is conserved. But what doesn't have to be conserved? Volume doesn't have to be conserved. It coincidentally might be conserved. Now you can interpret the coefficients as volumes if they are gases. That's a different topic than saying volume is conserved, because you can clearly see it's not, because you have 9 volumes on the reactants and 11 volumes on the products. All right. Another thing is molecules don't have to be conserved. Because again, you can see that 9 molecules on the reactant side does not equal 11 molecules on the product side. But those are ways you can interpret this balanced equation. The coefficients can be interpreted as representative units, in this case, molecules. But that doesn't mean they're conserved. Just want to make that clear, that conservation is not the same thing as interpretation of coefficients in a balanced equation. So to quickly sum it up, coefficients often represent moles or representative units or volumes if they are gases. Conservation is of mass, and in the simplest case, it's the number of atoms that make up the mass